Right, now we move on to matrices. But first of all, we need to fix some conventions. Suppose we have a matrix M, such as, let's see, 1, 1, 2, negative 1, 7, 2. So this is just one example. We want to represent a matrix such as this in a more abstract form. So, for example, in this case, we may write M11, M12, M13, M21, M22, M23. So in this case, M11 corresponds to 1, M12 corresponds to this 1, M13 corresponds to this 2, and this corresponds to this, M22 corresponds to 7, M23 corresponds to 2, and so on. So this first index corresponds indicates the first row, or the position in the row, either 1 or 2 in this case. And the second index indicates the column. Okay, so if this is one, second index is 1, that means the first column. If the second index is 3, it means the third column, and so on. But writing all elements like this explicitly is tedious, especially when the matrix is very large, like 100 by 100 matrix. So in that case, we may write like Mij, where it is understood that I runs over all the rows and J runs over all the columns. So in this case, I runs from 1 to 2 and J runs from 1 to 3. Okay? So a matrix, if we write M equal to parentheses M lowercase mij, that means elements of this matrix capital M are these lowercase mij's, where I and j are appropriate positions in the rows and columns. And also, if we have this matrix M, if we say this is a matrix without specifying elements like this, then M parentheses ij represents its element at ith row and the jth column. So ij element of matrix M is represented as this. So if we have matrix like this, define matrix like this, then we may write this M ij is equal to this lowercase mij. So the element is this. Okay. Now let us define matrix addition. So suppose we have two matrices, A, which is Aij, and B, which is Bij. And both of them are of the same size. Let's say n times m matrices. Then we define a new matrix C, Cij, again of the same size, n by m, by this. So each element of C is the sum of the corresponding elements of A and B. Okay, so this defines all the elements of C, matrix C. So this we call matrix addition. So we add two matrices A and B to define a new matrix called A plus B. which is renamed as C. So we could write C is equal to A plus B. And this really means each element of C is the sum of elements from the corresponding elements from A and B. Okay. Another way to express this addition is this: A plus B, which is a matrix and whose ij element is the sum of Aij and Bij. Oh, sorry, Bij. Okay, let's see an example. So if we have two matrices, 1, 1, 2, negative 1, 7, 2, so this is a 2 by 3 matrix, and another matrix of the same size, 3, 2, 1, 4, 5, 6. So if we add these two matrices, then the result is a new matrix. So 1 plus 3 is 4, 1 plus 2 is 3, and 2 plus 1 is 3. Negative 1 plus 4 is 3, and 7 plus 5 is 12, and 2 plus 6 is 8. So we simply add each corresponding elements. Next, we want to define matrix multiplication. So let's say A is a matrix which has the size of n by m. Okay, and B is another matrix which has the size of m by p. So they have different sizes, but what's important is the number of columns of A is the same as the number of rows of B. Okay, so this m and this m, they are the same m. Okay, then we define a new matrix C, which has the size of n by p. So this n is this n, and this p is this p. Okay, and so each Cij is defined as the sum over k and m a I k b k j. Okay, so this is a little bit tricky. It may not be so intuitive, but it turns out that this definition of matrix multiplication is very useful. Okay, so this means this. So just write a little bit more explicitly that this summation is I1 times B1j and I2 times B2j and so on, and up to AIM BMJ. So another way to write this is we write A B. So this is matrix multiplication. Okay, so in this case we write C is equal to AB, and AB ij element of the product AB is defined as this summation AIK and BKJ. Okay, so more intuitively, if we have a matrix of this size, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, then we have a matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is n, this is m, this is m, and this is p. Oh, this is p. So each row of the first matrix, okay, this matrix is A and this matrix is B. Okay, is so each row is multiplied with each column. So first, from the first row, we pick the first element, and first row of A, we pick the first element. And from the first column of B, we pick the first element. Then we multiply these two elements and add that to the product of the second element with second element. And third element times third element, fourth element times fourth element, and so on. And ninth element times ninth element. And we take all the sum of these products. Then that will give you the one element of the product. So the product will have the size of 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. So the number of rows of the product will have the same number of rows as the first matrix, and the number of columns of the product it had 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So this is n and this is b. So this is same as this, and this n is same as this n. So the result of this times this becomes this element. And the result of this times the second column, we multiply each element and take the summation, becomes this element. Okay, first row, second column. First row, second column. And for example, in this case, let's say fourth row and 1, 2, 3, 4, 5, 6, sixth column becomes fourth row and 1, 2, sixth column. Okay, so this times this results in this element. Okay, so let's see one example. Again, let us have 1, 1, 2, negative 1, 7, 2, and 1, 0, 0, 1, 2, 3. Suppose we have these two matrices. Then the result of this multiplication is, so we multiply this times this, this times this, this times this, and add them all. And the result should be, so 1 times 1, 1 times 0, 2 times 2, and add them all, and the result is 5. And similarly, we multiply this times this, this times this, this times this, and add them all, and the result is 7. The result is 7. And then we multiply this times this, this times this, this times this, and add them all, and the result is 3. And then we multiply this times this, this times this, this times this, and add them all, and we get 13. So we have 2 by 2 matrix as a result. Okay, so it is important that the number of columns in the first matrix is the same as the number of rows in the second matrix. A number of rows in the second matrix, yes. Otherwise, we cannot define multiplication. Okay. Okay. Next matrix operation is called transpose or transposition. So let's say we have a matrix A, which is an n by m matrix. Okay, then we define its transpose, written as AT, to be a, so this is n by m, then transpose is m by n matrix. It's a m by n matrix where each row of A becomes each column of A transpose. So that is this AJI. Okay, so this A is the same as this A. Okay, so we swap each row of A with a column of A transpose. So in other words, each element of A transpose, so A transpose ij element is the same as A's ji element. Okay, so here is an example. Again, let's say we have 1, 2, 1, 1, 2, negative 1, 7, 2. Its transpose is this. So 1, 1, 2, negative 1, 7, 2. So each row becomes a column. So this is transpose. And here's a simple lemma regarding transpose. We have this relationship. Transpose over transpose is the original matrix. I think this should be quite trivial, but let us prove it, which is actually quite easy. So transpose of transpose. Let's say we pick ij element of this. Then by definition, it is the ji element of this matrix. So A transpose is ji element. But by the definition of transpose of A, then it should be the element of it's ij element of matrix A. So therefore this is equal to this, which means every element of A transpose transpose is equal to the ij element of A. So that means this. It's done. Okay, now consider this example. Every row vector such as A, A1, A2, AN can be considered as a 1 by n matrix. So let's say we have two such vectors, row vectors, B1, B2, Bn. Then if we take the transpose of B, then that becomes a column vector. So we can multiply these two matrices. So this is a matrix. Matrices. Okay, so we can calculate this product, matrix product. So that is A1, A2, AN by B1, B2, Bn. So that becomes, so this is A1 times B1, A2 times B2, and so on, and AN times Bn, and take the summation. So the result becomes this: A1 B1 plus A2 B2 plus, and so on. But as we have studied already, this is nothing but the dot product between A and B. Okay. Of course, this is this is just one number, so this is one by one matrix, which is same as scalar. Okay. So we can generalize this observation in the following manner. So if we have a matrix, general matrix A, Aij, then we have something like A11, A12, and let's say this is n by m matrix. So 1m, A21, A22, A2m, and so on. So N1, An2, Anm. Okay. Now we consider each row as a vector. Okay. So this can be seen as a column vector of row vectors, so to speak. So let's call this A1, A2, and AN. Okay. So this means this A1 is equal to the first row, this A2 corresponds to the second row, and AN corresponds to the nth row of this matrix. Okay. And now pick another matrix. So this is wait a minute. A is an n by m matrix, and consider B, which is made of Bij's, and this has bunch of elements, but now let's see, B11, B12, and so on. And suppose we have P columns. So B21, B22, and B2P, and BM1, BM2, BMP. Okay, and this time we regard each column of this matrix as a column vector. Okay, so let's say this is B1 transpose, B2 transpose, and BP transpose. Okay, so this B1 is a row vector, so its transpose is a column vector, which corresponds to this corresponds to the first column, and this corresponds to the second column, and so on. Okay, so the number of columns in A is m, and the number of rows in B is m. So we can multiply them. So if we calculate A times B, so this means A1, A2, AN, times B1 transpose, B2 transpose, and BP transpose. So if you multiply this, you will find that this is actually equal to A1 B1. So this is a scale scalar product, okay, or dot product. I think I would write in the next page. So this is equal to the one element becomes A1 times B1, and two element becomes A1 times B2, and so on, and A1 times BP, and the second row becomes A2 times B1, A2 times B2, and A2 times BP, and so on. So this continues. AN times BP. So this is a N by P matrix, and each element is a scalar product between some AJ and some AI and some BJ. Okay. Now let us examine some of the laws of matrix algebra. In the following, I assume that all of the matrices have compatible sizes when they are added or multiplied. So let's say A, B, C are matrices of appropriate sizes. Then we have the following rules. A times B plus C is equal to AB plus AC. So this is a distributive law. And the same for multiplication from the right. So this is multiplication from of A from the left, and this is multiplication of C from the right. C and BC. So these two laws are distributive laws, and the third one is the associativity of matrix multiplication. Okay, and of course it should be obvious that matrix addition is also associative. Okay, it's associative. So multiplication is associative, and matrix addition is also associative. Okay, and these can be checked very easily. So first, calculate the left hand side, each element of the left hand side and each element of the right hand side, and compare them to see if they are actually equal. Okay. To see this, let us prove the first one, for example. So A, B plus C. So its ij element is this. So B plus C is a matrix. Okay, so by definition of matrix multiplication, we multiply A times B plus C. Okay, so that was this. From K, we don't specify the range of K, but just assume this runs over appropriate range of index. Okay, so this ij element of this matrix product between A and B plus C is this A K and B plus C K J, right? But addition of matrix is just element-wise addition. So that means this is a ik. So we can just kind of distribute the indices bkj plus ckj. But this is just addition of real numbers, and this is just a multiplication of real numbers. So we can apply the distributive law of real numbers to find ak times bkj plus aik times ckj. Okay, and we can split the summation, which is bkj plus aik ckj. But each of these summation is the element of matrix product. So that is AB, an ij element, and this is AC, ij element. Okay, therefore we have this result. And you can prove the second result very similarly. And let's prove this third one, associative law of matrix multiplication. Okay, so let's see. So what we want to prove is this. A, B, C is equal to A, B, C. So just calculate products in two different ways and compare the results. That's the basic assumption, basic strategy. So let's see. Let's first calculate this one. So A, B, C. Let's find the ij element of this one. So this is the matrix product between this matrix, AB. AB is one matrix, okay? It's a result of matrix multiplication, but which is a matrix. And another matrix is C. So by the definition of matrix multiplication, this is something like AB, IK, and C, KJ, right? Then we expand this multiplication. And, well, so let's see. Let's consider this first. ABK, IK. This is a matrix product, so using another symbol for the index, this is A, I, L, and B, L, K. So this I comes here, this K comes here. Okay, and the new index comes here in between. Okay, so plug this result into here. Okay, therefore this becomes K L A I L B L K times, oh, maybe I should write this, and C K J. Okay, but we can apply distributive law of real numbers. So this becomes summation over K, summation over L, and A, I, L, B, L, K, and C, K, J. So this is the result of this multiplication. And if you apply the same step for this one, so what's the ij element of this? So let's say il, and we can use any index, l or k or whatever, as long as it doesn't overlap with ij, I and j. So that's bc and lj, but this one is this k b l k times c k j. Okay, and we can apply the distributive law. Then it becomes L K A I L B L K C K J. And the order of summation doesn't matter, so we can just change the order. First sum over L, then sum over K. It's the same thing. So compare these two results, and they are exactly the same. Therefore, we have the distributive law. I mean, associative law. Okay. And the last one, the associativity of addition should be very trivial. This one should be very trivial, and you should try it yourself. Next, we study identity matrices and matrix inverses. But first, let us introduce a convenient notation called Kronecker's delta. Let us define it. It's called Kronecker's delta. Delta. Okay. Kronecker is a German mathematician of the, I think, 19th century. Anyway, we define this symbol delta. This is a Greek letter, lowercase delta, ij, which is 1 if I is equal to j. Otherwise, 0. Very simple. It's very simple, but it's very convenient. It's very handy. So, based on using this, let us define the identity matrices. So, n by n identity matrix is the n by n identity matrix is written as In, whose elements are Kronecker's delta. Okay, so this means when I and j are equal, it is 1. If I and j are not equal, then it is 0. So here are some examples. So I1, so this is one-dimensional identity matrix, 1 by 1 identity matrix, which is just 1 because there's only one element. And I2, which is 2 by 2 matrix, is 1 0 0 1. And I3, which is 3 by 3 matrix, is 1 0 0 1 0 1 0 0 0 1. So as you can see, you find ones on the diagonal. So these are called diagonal elements. And everything else are called off diagonal. And those off diagonal elements are 0. Okay. So these are, oops. These are diagonal. And everything else are off diagonal. Sometimes we write this way. So I3 is 1, 1, 1, and big 0. So big 0 means everything off diagonal are 0. Okay, so that's the identity matrix. Now, here's an important property of the identity matrix. So here's a theorem. Let X be X Xij be any n by n matrix. Okay, and then we have this. The identity matrix times X is equal to X, which is equal to X times identity matrix. So this means multiplication by identity matrix does not change the matrix X. Okay, let's prove this. I mean, we can just check the elements of this matrix multiplication. Okay, so Ix, its ij element is this according to the definition of matrix multiplication. This is In, Ik, and X, Kj. But ij element of X matrix X is just Xij, and ij element of the identity matrix is Kronecker's delta. So this is equal to delta Ik and Xkj. But this delta Ik is 0 unless I is equal to k. So if k runs from 1 to n, it becomes this delta becomes 1 only when k is equal to I. So therefore everything else is 0. So we have x, k is I, and j. So this is the ij element of the matrix X. Therefore we have this equality. And the other equality can be proved in a similar manner. So we calculate this matrix product and deduce that this is equal to X. And next we introduce another convention. Let's say we write Mn of k to mean the set of all n by n matrices. N by n matrices over k over k. K is a set. We usually use real numbers, so this means all the elements of these matrices are from this set. So we usually work with this set of matrices, and actually this is the only matrices we are going to deal with as far as square n by n square matrix is concerned. So we just abbreviate this by n in the following. Okay, then based on this notation, let us define the matrix inverses. So inverse matrix. So suppose we have a n by n matrix X, then Another matrix, n by n matrix, is a right inverse of x if we have x times y is equal to the identity. Okay, right here means we are multiplying y from the right of x. Okay, because in matrix multiplication, the matrix multiplication may not is not commutative. Okay, so in general we don't have xy equal to yx. They may be different. So here's right inverse, and we say left inverse. Y is a left inverse if y times x is the identity. Left inverse. Inverse. Okay. And mm, and we cannot prove this right now, but you should note that uh, if both if both right and left inverses exist inverses of x, they are equal. They are equal. So this means if y is the right inverse and if z is the left inverse of x, then y is equal to z. Okay, so this is one point. And another point, if there are two left inverses, then they are equal. So let's say if y is a left inverse and also z is a left inverse, then we have y is equal to z. So this means inverses are unique. Therefore, we write inverses as x to the power of -1. So we write x inverse as this. So in other words, uh, so if there are left and right inverses, they are equal, and if there are two left inverses, they are equals. So in any case, the inverse is one inverse of a matrix is unique, and there are no other inverses. Okay, therefore we can uniquely write the inverse of x as this. So we have x inverse x is the identity, which is equal to x times x inverse. Let's consider a very easy example. So M1 is one by one matrices of real numbers. So this is actually the same as the set of real numbers. So if we have this matrix, one by one matrix from M1, then its inverse is, so C inverse is 1 over C if C is not equal to 0. Right? So if you multiply this times C inverse, C inverse, this is C times 1 over C, and this is just one element, so this is C times 1 over C, which is 1, which is the identity matrix of one dimension, one by one identity matrix. Very simple. Now, consider, oh, by the way, when C is equal to 0, there are no inverses, right? Because whatever the other matrix is, the multiplication results in 0, so it can never be the identity matrix. So next, consider M2. So that is 2 by 2 matrices. Okay, first of all, this matrix, 0 matrix, all elements are zeros. And this has no inverse. No inverse. So, why? Because if you multiply any matrix with this 0 matrix, the result is always 0 matrix. Therefore, it can never be equal to the identity matrix. So there are no inverses for this. Okay, and now suppose x is equal to a, b, c, d. And we want to find the inverse of this matrix. So let us define delta, so this is capital letter delta, AD minus BC. And if this delta is not equal to 0, then the inverse matrix of X is given as this: D over delta minus B delta and minus C over delta and A over delta. And you can check this is indeed the inverse matrix of X by calculating the matrix product X times X inverse, or for that matter X inverse times X. Either is okay, so it should be equal to 1 0 0 1, which is the identity matrix of 2 by 2 matrices. Okay, you should just compute the matrix product. And if this delta is equal to 0, then no inverses. There is no inverse. So you can see that this quantity delta plays an important role in determining the inverse of a matrix. So let us define this, give it a name. It is called determinant of a matrix. Of 2 by 2 matrices. So this, if let X be a 2 by 2 matrix given by A, B, C, D, then delta AD minus BC is called the determinant of X, and written as det X. Okay, so det X, determinant of X, is AD minus BC. So that is 1 element times 2 element minus 1 element times 2 element. So that's the determinant of 2 by 2 matrices. Now we see an example of an application of matrix inverses. Okay, so let's consider this problem. Simultaneous linear equations. AB plus BY is equal to P, and CX plus DY is equal to Q. And we want to solve these equations for X and Y. Okay. So these equations can be summarized using a matrix and vectors. So let us define A as the matrix of these coefficients A, B, C, D, and a vector x as x and y. It's a column vector, and also a vector p of these right hand sides p, q. Okay, if we write like this, then these equations can be summarized as this: a, b, c, d times x, y equal to p, q. Right? So that is a x is equal to p, q, p vector. So if a inverse exists, then we can solve this equation by multiplying both sides by a inverse from the left. So that is a inverse times ax is equal to a inverse times p. But actually you have seen that matrix multiplication is associative, and a vector is also a matrix in a sense. So we can move these parentheses to a inverse and a times x. But this is the identity matrix. So when we don't care about dimension, we just don't write this 2, but just write I. Right? And A inverse P. But multiplying by the identity matrix doesn't change the vector. So this is equal to this. Okay, so now this x is x and y, and this is some vector resulting from this multiplication. So effectively, we have solved these simultaneous linear equations by using the matrix inverse. Okay, so let's see a concrete example. We have, let's say, 2x plus y equal to 1 and 3x minus y equal to 0. So we want to know the values of x and y. So here, A is the matrix consisting of these coefficients, 2, negative, positive 1, 3, and negative 1. And the determinant of this matrix is 2 times negative 1, so 2 times negative 1 minus 1 times 3, which is negative 5, which is not 0. Therefore, by the formula we have given previously, the inverse of A is given as 1 over 5, 1 over 5, 3 over 5, and negative 2 over 5. Okay, so x and y is the inverse of A times 1 and 0, right? So 1 and 0. So this matrix and 1 and 0, this is so this is this times this plus this times this, which is wait a minute, this times this times this, so this is 0. So the first element is 1 over 5, and this times this times this, so second element is 3 over 5. So therefore x is equal to 1/5 and y is equal to 3/5. So we have solved these simultaneous equations. So far we defined the determinants for 2 by 2 matrices. Next, we want to generalize the concept of determinants to any dimensions. So for general n by n matrices. But this topic is pretty complicated and it's a big topic, so I will explain this in the next separate video. See you later.